Good morning, good afternoon, and good evening. Thank you for joining us. My name is Maureen Price, and I will be the moderator for today's webinar. I lead Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. Every one of the Innovation Builders team and the speakers on this call are remote workers, and we applaud their ability to find the time to share their knowledge in addition to serving their clients while juggling the intersection of their career and home lives. Today's technical presentation is about carbon capture and how we can build a better world with it. The goal of today's presentation is to help you. We will talk about how carbon capture affects you directly as an owner-operator, using practical information on costs, benefits, and opportunities. To that end, our agenda is focused on answering the questions that you may have. Why consider carbon capture and what opportunities are available? Who has been acting on those opportunities? What options do you have for collection and disposal? How to integrate those options with the goals of an existing facility? And of course, an understanding of the capital cost breakdown based on real-world experience. We have an expert today with us to help answer those questions. Our speaker today is Fluor Senior Fellow Michiel Baerends. Michiel has over 22 years of process engineering design experience at Fluor. His experience covers most refinery processes as well as all aspects of sulfur processing, including sulfur recovery, tail gas treatment, amine, and sour water. He also has substantial experience in gas purification and carbon capture. In his free time, he enjoys the study of post-1500 world history and collecting ship models. Fluor has a strong safety-driven culture. As such, it is customary for us to start our meetings with a safety topic. I'll ask Michiel to unmute his line to share a brief safety topic and begin.
Well, thank you, Maureen. So my name is Michiel Baerends, and as Maureen said, I'm going to start this discussion with you for the next hour or so with a safety topic. The topic is about the hazards that are inherent in carbon capture facilities as they handle concentrated CO2 streams. Now, although CO2 is not classified as toxic or hazardous, at very high concentrations, it can actually be dangerous. It dissolves in blood, which is harmful. Now, the PEL, the permissible exposure limit, is the concentration that is still acceptable for continuous exposure during the entire workday. So this level is at 0.5 volume percent, which is equivalent to 5,000 ppm. And for reference, you can compare that to the atmospheric background CO2 concentration, which is used to be less than 300 ppm before the Industrial Revolution, and today is approaching 400 ppm. Now at higher levels, about 4%, you're at risk from disorientation and dizziness, and at 10% or 100,000 ppm, even a short-term exposure can cause rapid loss of consciousness and even death. Our mitigation relies on multiple layers of protection. First of all, good design practices exist to minimize any risk of leaks. The next layer is training, so that everyone present in a capture plant is fully aware of the risks and knows what to do in case of an alarm going off. An important one also is adequate ventilation of enclosed spaces, as these are the locations where CO2 can most easily accumulate to dangerous levels. And finally, there are portable CO2 monitors that give operators an early warning at the actual location where they are. Now, when we think about moving forward from the current pandemic situation, we should consider both how to address climate change, while at the same time sustaining our economies that are very hard pressed as it is. Transitions on an enormous scale, and the so-called energy transition is certainly in that category, are not going to happen overnight. So for a considerable amount of time, the world is going to need carbon-based fuels and feedstocks, and using these is going to result in the formation of CO2. In addition to refining and petrochemical industries, there is a number of quite vital industries. Think of the manufacture of cement for construction, glass, waste incineration, industries that inherently generate CO2 in their processes. And we believe that carbon capture can be a key technology, a proven technology, that can enable such industries to undergo a practical and achievable transition to a future with much less CO2 emissions. In the meantime, the public, acting through their elected governments, is going to continue to push for results in the form of lower CO2 emissions, using a carrot and stick type of approach. So carbon capture is an approach that we think will fit to a lot of industries, enabling them to adapt themselves to this low CO2 future, while actually continuing their important business operations, important not only to these industries themselves, but also to society at large. Also, carbon capture is really a hedge. It hedges industries against more and more aggressive legislative pressures for lower CO2 emissions in the future. So what opportunities are out there? So as said, carbon capture is really a way to maintain and adapt the existing core business to new regulatory pressures. And to support this adaptation, there will be combinations of direct government support, I call it subsidies, tax credits, and cap and trade market systems, CO2 taxes and fines, to either help reduce the economic cost of implementing carbon capture, and in some cases actually provide a positive economic opportunity, while still maintaining the pressure to do something. A nice example of such an opportunity, a recent one, is emergence of so-called carbon neutral LNG. That is LNG that is produced while capturing all the CO2 from the exhaust of the gas turbines that drive the liquefaction process. And this carbon neutral LNG is sold at a pretty good premium over normal LNG. And so maybe an interesting opportunity for LNG producers. And many of the incentives that we're talking about, they're tied, of course, to government regulations, and they can and will change over time. We do expect that the penalties for continued emission will only go up in the future. And that on the other hand, the incentives are going to be the most favorable, the most attractive to early actors, to industries that adapt early on. Now, carbon capture is certainly not new, far from. In fact, Fluor's own key technology, EFG+, that I will discuss later on, stretches back to the 1980s, so decades ago. And many facilities using different technologies have been built to date and have also operated over many years. All the round circles on this map of North America represent operating plants. And as you can see from the colors, they cover different industries. The orange is power plants, the green natural gas facilities, and the green other industrial plants, including even fermentation plants. One of the reasons why North America has got so many operating carbon capture plants is that they have a number of CO2 pipeline systems connecting the capture plants to the sites for geologic injection to leave the CO2. These pipeline systems exist, for example, along the Gulf Coast, and also a new one has been streamed in Alberta in Canada, where you see a cluster of capture projects. Now, the next one, Asia Pacific, there we see two operating facilities, one being the large Gorgon LNG project on the Australian coast, and another smaller one in Japan. Then in Europe, Africa, the Middle East, you also see a number of operating plants, most of them natural gas-based, and one in Abu Dhabi, which is a steel mill. Now, zooming in on the round area, that is the area around the North Sea, and this is where a lot of current planning activity is centered. And that is related to the fact that the North Sea is one of the more promising sequestration locations to leave the captured CO2. But further on that, one of the absolute keys, of course, for any carbon capture facility is to find a good destination for the captured material. Some chemical processes actually benefit from additional CO2, and I'll show an example of that. There are new chemistries under active development, not commercial at very large scales, but they create a further potential for use of the captured CO2 in the future. Food and beverage industries, they've been a long-time user of CO2, but on a fairly modest scale. When you look at very large-scale capture projects, people generally look at geologic deposition of the CO2 of some sort, either in conjunction with enhanced oil recovery or permanent storage, which can either be in empty oil and gas fields or in so-called saline aquifers. Now here's an example on methanol plants. Such plants, also ammonia-urea complexes and other syngas processes, are possible users of CO2. The methanol process actually benefits from adding additional CO2 as it adjusts the syngas composition, the feed gas composition to the methanol loop to produce more methanol products. Fluor has recent experience with designing a world-scale methanol facility to also recover CO2 from the flue gas from the steam reformer furnace, increasing the yield of methanol. So that is effectively converting waste CO2 into a valuable product. Now, expanding on this concept, it's possible to combine recovered CO2 with green hydrogen to produce key chemical building blocks, or even fuels, so-called e-fuels, without using a hydrocarbon feedstock. And as you can see in the picture, so the first plants, albeit on a very small scale, are already operational. This is in Iceland. So in future, this could be an important outlet for captured CO2. Now, a bit closer to home for me, the Netherlands. Yeah, we have a large-scale greenhouse industry that can use enhanced CO2 levels inside the greenhouses to stimulate plant growth rate. There is a pipeline system called OCAP that uses CO2 captured from a refinery and a fermentation plant in the Rotterdam area that feeds these greenhouses through the pipeline system, as you can see at a fairly significant scale. And that is working today. Now, as mentioned, very large-scale capture projects really look to store the CO2 underground. Now, large formations of so-called porous sedimentary rock with an appropriate cap layer on top, and that cap layer is important to ensure that the CO2 stays where it should stay. Such formations can store a lot of CO2 deep underground. And the good news is that this basic geology exists pretty much worldwide, presenting worldwide possibilities for carbon storage. Look here at the map. The darker colors, they represent the thickest such formations, presenting the best potential for CO2 storage. And what's interesting is that the very same rock formations that are good at storing CO2 are also good at storing oil and gas. So you see that some of the dark areas in this picture, take for example the Middle East or Kazakhstan, Central Asia, the US Gulf Coast, but they're also the well-known oil and gas producing regions. Now, zooming in on Europe, we see there in green, in the North Sea area, you see a prevalence of such hydrocarbon fields. Many of them are no longer producing, and therefore they're available for CO2 sequestration. What it also shows, this picture, is the blue areas. They represent so-called saline aquifers into which CO2 could be injected permanently. And as you can see, these exist more widely than just the oil and gas reservoirs. In order to get the captured CO2 to the geological destination, pipelines are a very good way. And ideally, such pipeline projects are covered under a shared arrangement between different capture plants or even a public or semi-public arrangement. And that allows to take the CO2 deposition portion of the whole equation out of the picture and have it owned and operated as a way of public shared utility system. and making it much easier for every potential carbon capturer in the area to consider carbon capture, knowing that there will be a home for the captured CO2. Here on this slide, you see the Portals and Atos pipeline systems in the Netherlands again, both under design development, bringing CO2 from the Rotterdam and Amsterdam industrial clusters to the sequestration locations under the North Sea. I think it's instructive to take away something on orders of magnitude. The choice of CO2 destination is going to depend largely on the amount of CO2 that is actually captured. So for small-scale capture plants, there may be a good fit with greenhouses or beverage facilities. Whereas for very large-scale systems, think of the order of 1 million ton per year. That is a fairly typical size for large commercial facilities. For now, geologic storage is the way to go. Okay, so what configuration options are available? Well, carbon capture can be divided up into 3 main categories: pre-combustion, post-combustion, and oxy-combustion. We believe that all of these flavors have their own applicability, but in this presentation, we only focus on the first 2. So starting with pre-combustion capture, some processes like hydrogen production from natural gas or even oil or coal produce CO2 as a byproduct. And in these units, it's possible to capture the CO2 from a high-pressure concentrated process stream. You may have heard of the term blue hydrogen. That refers to hydrogen generation with carbon capture included. The hydrogen product from such a blue hydrogen plant can be used as carbon-free fuel. Removing CO2 from natural gas, in case the natural gas contains CO2, is actually also a form of pre-combustion capture, although a very partial form of capture if the natural gas is then later used for combustion. Now, for pre-combustion capture, you use liquid solvents of different types, absorbing the CO2 from the high-pressure process stream and being regenerated at low pressure to collect the CO2 product. And it's quite feasible, actually, to retrofit current hydrogen plants in this manner, converting them into blue hydrogen production without actually impacting the important production of hydrogen. And our first example, in fact, is a facility that did exactly that. So the Quest carbon capture project is located in a heavy oil upgrading facility in Alberta in Canada. This facility has got 3 large hydrogen production plants generating some 400,000 normal cubic meter of hydrogen. And all that hydrogen is used to upgrade the heavy oil by hydrocracking. Now, the project uses an amine solvent technology with a central amine regeneration facility, which is common to the different hydrogen plants, each of which has a dedicated absorber. The amine used is a Shell-named brand called AddEpX, which includes NDEA in the formulation, and it's an aqueous solution. So this was a commercial scale facility, and it was partially funded by the governments of Alberta and Canada. And so a typical example of direct subsidy support. And the aim was to demonstrate both the capture side on a very large commercial scale, and also the safe sequestration of the CO2 into a local saline aquifer. Now, Fluor played an integral role in this whole project development, together with Shell in their capacity as the site owner as well as the technology provider. And our involvement went all the way from conceptual design through detailed engineering, construction, and project completion. As you can see in the pictures, the scale of this facility is definitely world-class commercial. You just can zoom in on the picture and look at the size of the construction workers that are standing on the ground next to the columns. On the left, you see the central amine regeneration facility, the large amine regeneration tower. And on the right, you see 2 amine absorbers, one for each of 2 hydrogen plants. Now, switching gears to post-combustion capture. Post-combustion is added on the flue gas from pretty much any combustion-related type process. The flue gas coming in on the left bottom of the picture. It's first cooled in a direct contact cooling column. And that column can also be designed, if necessary, to take out certain impurities from the flue gas. Then there's a blower that pushes the flue gas into the absorber column, and that is where the CO2 absorption happens with counter-current contact against an amine solution. And on the right, you see the stripper, in which the CO2-laden amine solution is regenerated and then returned to the absorber. In the bottom right of the picture, you see a solvent reclaiming system, and that is needed in every post-combustion system to maintain the right solvent quality. This is necessary because in post-combustion systems, there's always some presence of oxygen, and oxygen gradually degrades all amines. There are various other design features that we've developed over time to minimize energy consumption and also minimize emissions. A real key advantage of post-combustion is that you can really bolt it onto any process that has a fired heat source. So you can think of large refinery, fired heaters, FCC units, hydrogen plants, but also power plants, be it based on coal or natural gas, cement factories, waste incineration plants, you name it. And those are just some of the applications where post-combustion capture has been or can be applied. Our own ECONAMINE FG Plus technology is an example of an amine technology that was specially adapted to post-combustion applications. Any carbon capture system will always operate best with high CO2 concentrations and low oxygen concentrations. Because high CO2 is conducive to absorption, and low oxygen means less degradation. Specialized systems like our ECONAMINE FG Plus are specifically adapted to handle the conditions of each flue gas. And as an example, we've used this technology commercially with a rather challenging flue gas stream, being the exhaust of gas turbines, because such flue gas has a high amount of oxygen and a relatively dilute CO2 concentration. On the other extreme, looking at CO2 concentration, we also see applications where the CO2 concentration can go as high as 20% volume, sometimes even towards 30 for specific reasons, which is quite extreme actually. So most, let's say, middle of the road applications are closer to 10% CO2. Now on this picture, you see the commercial facility that treats gas turbine flue gas. You see a large amine absorber in the middle with a vent pipe to atmosphere. To its left, you see a smaller stripper with associated reboiler to boil the amine to drive out the CO2. And on the right, the short stocky column is the flue gas cooling column. And all the way on the right of the picture, there you see the stack from which the flue gas was taken in. Now we also demonstrated the EFG Plus system on very different flue gases. For example, an FCC flue gas, and as you see in this example, flue gas from coal-fired boilers. Just demonstrating the ability of the solvent to handle very different flue gases with different concentrations of oxygen, CO2, and also with different specific impurities. Now, as already alluded to, handling amine degradation is a key challenge for every post-combustion system, and that is related to the oxygen content of the flue gas. We've developed proprietary techniques, so the reclaiming that I mentioned earlier, to keep the amine solution clean and in good shape. And the picture in the middle here shows the appearance of the amine solution in this plant after a significant amount of online time on a coal-fired boiler flue gas. And from its appearance, you can clearly see the effectiveness of the solvent cleanup system. Now to summarize, post-combustion capture can be bolted onto many different processes. In some cases, we can also combine different flue gases in a common single absorber, especially, of course, when the flue gas sources are not too far away, because bringing flue gases to other locations might involve large ducting. So you can think of clusters of fired heaters in refineries or petchem plants. Important, this is proven technology, years of direct operating experience behind it. So now that we've highlighted some commercial applications that are in operation today, we will now talk about costs. One way to shed some light on costs, especially in a comparative sense between pre- and post-combustion systems, is to look at a plant where you can do the capture in one of both ways. And a modern steam reforming-based hydrogen plant is exactly such an example. Here you see a scheme of the plant without carbon capture. Natural gas coming in from the left goes through a reformer and a shift reactor, where the natural gas is converted to hydrogen and mainly CO2. And the hydrogen is then produced in a pure form from the PSA, with the CO2 sent to the fire side of the reformer, together with additional natural gas as required to meet the reformer heat balance. So the CO2 that ultimately comes out of the stack from the reformer firebox contains CO2 both from the process itself as well as from the additional combustion. Now, pre-combustion capture simply adds a capture system in the middle of the process flow, so between the CO shift and the PSA. And this is, in fact, the exact configuration that was used on the Quest project, of which you saw some pictures. So this captures the CO2 made in the process, but it doesn't capture additional CO2 produced in the reformer firebox. And overall, in hydrogen plants, pre-combustion capture systems capture some 50 to 60% of the CO2 of all the available CO2. Instead, post-combustion adds the capture system on the flue gas from the reformer firebox. And now all of the CO2 molecules that are made in the facility have to pass it. So this enables nearly full capture of all the CO2. Now the capital cost of any carbon capture system is, of course, a direct function of the amount of CO2 that is captured. And the comparative figures on this page and the next, they compare two facilities, assuming that they capture the same amount of CO2, 2,500 ton per day captured. As we noticed, the pre-combustion system only captures about half of the available CO2, whereas the post-combustion system captures nearly all. So as a result, to make the capture system have the same capacity, the host hydrogen plant needs to be twice as big for the pre-combustion system. Now, focusing a bit on the one of the key equipment items in any capture plant, that's of course the CO2 absorber. There are some important differences between pre and post-combustion here. The post-combustion system absorber runs at a much lower pressure, effectively atmospheric pressure. And as a result, the actual volume flow rate of the gas through the absorber is as much as 25 times higher than it is for pre-combustion. In pre-combustion systems, for reference, the absorber runs at considerable pressure, let's say 20-25 bar or so. In the middle, the diagram compares the absorber diameter for both cases. And what you see there is that the post-combustion absorber has a roughly twice bigger diameter, but the difference is not as extreme as the difference in gas volume flow rates. And that is related to a higher difference in density between gas and liquid in the post-combustion system, which is good for the capacity of the internal packing. Now, if you look at construction cost, a very important factor is, of course, the design pressure of the column. As stated, for pre-combustion, the design pressure is much higher, resulting in much higher wall thickness for pre-combustion. There will always also be a lot of site or project-specific factors, one of which is the question whether the absorber can be shop fabricated and transported to site, because it's a very large and bulky item, or whether it needs to be field welded at site. So that would also affect the comparison. On the next slide, we see an approximate capital cost breakdown across a capture plant, showing the capital cost of the different subsystems. And what is interesting here is that some of the areas that are not an integral part of the capture plant itself, so especially the CO2 compression, the pipelines to wherever the sequestration location is, and possibly any wells, the combined capital cost of that can easily exceed the whole capital cost of the capture plant. And that again nicely underlines the advantage of having a shared pipeline scheme in which to tap in. Now, for any comparison, of course, one has to look at the overall picture. There are important technical similarities between the two systems. The regenerator is fairly similar, related to a fairly similar amine circulation rate. And for identical CO2 amounts, of course, the whole CO2 handling, the compression is also the same. There are also real technical differences. The pre-combustion system needs high pressure amine pumping to get the amine to a high pressure absorber. On the other hand, the post-combustion system will probably require flue gas cooling, and most flue gases are fairly hot. It needs solvent reclaiming, as mentioned, and the absorber operates at low pressure. Now, overall, we find that the capital cost is actually fairly similar. And the same is true for the operating cost, of which steam for reboiling is always a very high proportion. An outstanding difference here that is maybe not as obvious and apparent is that for pre-combustion systems, as they capture only roughly about half the CO2 in steam reforming type hydrogen plants, any costs related to taxes on CO2 emissions are going to be very much higher for pre-combustion. And we think that such CO2 emission taxes or fines are only going to increase in the future. So that is a pretty key advantage of post-combustion systems in this case. Now, regardless of the technology that is used, next slide, please. A very important aspect is the integration of the capture plant into the overall facility. And that's really a key for project success. And to do that integration successfully requires the right experience and knowledge, not only in-depth knowledge on the capture technology, but also a very good understanding of what is happening in the existing host facility. And of course, a lot of intense collaboration between the different parties. And let's just show some examples. Any amine system requires steam for heating to reboil the regenerator, cooling water and power. Power to circulate the solvent and to compress the CO2. And one possibility is that you pull all these from the host facility. So this diagram shows a carbon capture plant, post-combustion, connected to an electrical power plant, coal-based, where steam and power and cooling water are pulled from the host facility. And you see there that steam was extracted from a side location of the steam turbine, which also then unloaded the vacuum condenser, the VC, making cooling water available as well for the capture plant. And in addition, the capture plant power requirements would also come from the host power plant. This is, of course, as you can say, parasitic. There has to be a derating of the output that the power plant can do. But such a scheme very clearly minimizes capital investment to a bare minimum. In some cases, we also see specific synergies that can be achieved, like shown in this picture, using low-level heat available from the capture plant. And in some cases, even using the condensed water from the flue gas cooling, which in some locations has value. Now, on the other extreme, perhaps, is elimination of the impact of the capture plant on the larger facility by using a purpose-built, a new COGEN plant to provide steam and power for the carbon capture plant. And you see that here on the right of the slide, the blue triangle. And so this COGEN plant makes available steam power for the capture plant, so that there's no derating of the host plant. Interestingly, you see that there is going to be an additional flue gas stream now coming out of the new COGEN plant, much smaller than the main flue gas stream, by the way, and it can be treated in the same amine absorber that treats the main flue gas. Now let's look at another example of how integration can work. Now pre-combustion, using the Shell Quest project as an example again. This slide summarizes the key project drivers on this project. They may not be so surprising, but for this kind of revamp projects, there's always interesting challenges to overcome. And by the way, what you see on the picture is the CO2 compressor. Now, the initial thinking on this project was to rigorously minimize the utility consumption of the capture plant. And to an extent, this utility consumption minimization goes at the expense of capital cost. In this case, however, what we found was that actually the host facility had sufficient utilities available for the capture plant at very low cost. So this realization provided an opportunity to refocus the design optimization of the capture plant. So we worked with the licensor in an early stage of the project, resulting in a CAPEX optimized design, a minimum capital cost design, rather than a minimum utility consumption design. And here you can see the resulting savings in CAPEX from that exercise, also some savings in footprint. So how did we come to that realization that utilities were actually available at low cost? Well, here's a schematic of a COGEN power plant that was part of this overall facility. It uses byproduct steam, shown in red on the left, coming from the hydrogen plants, and it can produce power and export low pressure steam. To produce more power, more steam has to be sent through the LP stage turbine and the downstream steam condenser, surface condenser. Producing more power then means that there's less LP steam available for export. However, we found it in this case, peak power production from this cogen plant was actually only needed in exceptional cases, much less than 5% of the time, when there were problems with the local electrical grid in that area. So during actual operation, during a more normal operation, more representative, only limited power needed to produce from this cogen plant, and a very significant surplus of LP steam was available, which they actually condensed in another condenser that you see between the turbine and the surface condenser. Of course, also using considerable amounts of cooling water. Now, because of the above reasons, as it turned out, we could integrate the capture plant into the existing system at very minimal capital cost, because we didn't need additional utility facilities. And also using available surplus LP steam and cooling water at no effective operating cost. Only when the host facility would require a lot of power in case of problems with the local electrical grid, only then would the cogen plant need to be ramped up to produce much more power. And at that time, insufficient utilities were actually available to the capture plant. So to cater for this scenario, again, less than 5% of the time, we designed the capture plant to allow it to temporarily stop operating. So we designed the capture plant to start and stop in a space of time of some 6 to 8 minutes or so, without impacting the hydrogen production. Once the demand for peak power is over, once the local electrical grid is back to normal, the CO2 capture plant can continue again as utilities are again available. As you can imagine, in practice, this ability to switch on and off certainly produce some interesting challenges, but they were overcome through good design and close collaboration. Another key project driver was maintaining the core business of upgrading heavy oil in this case, requiring a lot of hydrogen. So to do the revamp with minimal interruption during construction and also using minimal footprint. So to minimize construction work at site, and this was also related to the specific location of the site. up north in Canada, a very cold location, difficult to do construction in winter. We used a high extent of modularization, and that was successful. Also interesting on this 3D rendering is in the middle you see the two absorbers that you may recall from the earlier photo. You also see two stacks, and next to each stack you see a flue gas circulation system, circulating flue gas back from the stack into the hydrogen plant reformer firebox. And what the flue gas recirculation system effectively did is it ensured that the combustion side of the reformer would always see, let's say, the same conditions, irrespective of whether the capture plant is operating or not operating. Now, overall, this was quite a successful project, a proven success. Plant has started up a number of years ago and has been operating at nameplate capacity ever since. And maybe the best is that it was built on time and below the budget. Some concluding remarks, some takeaways. So before we get into the Q&A, let's just highlight a few things that I hope you can take away with you today. The first is our belief that carbon capture needs to be a part of the climate change solution. Fossil fuel use is probably going to decline, but it's definitely not going to go away anytime soon. And carbon capture is a technology that enables a practical transition to a low CO2 emission future. I hope we highlighted the options that you have available, options for where to go with the CO2, options for which technologies to choose from, and very importantly, hopefully also a better understanding of the opportunities and the importance of integrating the capture plant into your own facility. Last but not least, whether or not the actual incentives or penalties have fully crystallized out in your particular jurisdiction, we really strongly believe that it's a very good idea to start evaluating and studying today in order to be best prepared for the near future. Well, that's it from me so far. Let's turn it over to Maureen to see if there are any questions.
Thank you, Michiel. We do have a number of questions that come in, so are you ready?
I'm ready.
All right. The first question reads, how does the presence of particles in the flue gas affect the performance of the sorbents?
That's a very interesting question. If you're talking about post-combustion capture, and that is a more likely situation where there may be some particulates in some flue gases. Typically, pre-combustion capture, we see very clean gases that are treated. So in post-combustion capture, as you may recall from the flow sheet that we showed, there is a flue gas cooling column, the direct contact cooling column, which would take out some of the particles. Additional particles would be taken out by the amine system, and we could filter them out. You may also recall from the flow sheet that, as an integral part of the technology, we provide means of particle filtration. Now, whether or not the capture plant is the best place to take out particles, or whether it's maybe better overall to have a pre-step, to pre-treat the flue gas prior to entry into the capture plant, that is going to really depend on the amount of particles, the concentration of particles, and their nature. So it is something that has to be looked at for every specific case.
All right, great. Here's another one. How much potential do you believe physical solvents like ionic liquids have in reducing solvent regeneration and makeup costs?
That's a very interesting one. We are very aware of the fact that the numerous technologies are under development for carbon capture in the R&D stage. But the fact of the matter is that at this time, the only really proven technologies on a commercial scale are amine-based technologies, such as our own. So I do believe that in actual practice, most actual plants are going to rely on technology that is well proven. Having said that, of course, we very much welcome and are excited by further improvements. We continuously improve our own technology as well. So we very much welcome improvements to other new technologies as well.
Great. Here's another really good question. What removes the dissolved oxygen in the amine reclamation process? Or does the reclamation just remove the already degraded amine?
Yeah, the latter is correct. The reclamation removes the already degraded amine. It is also so that by selectively removing certain key impurities, the rate of degradation can also be lowered. Can be lowered very importantly, actually. This is a very key and core part of the post-combustion technology, as mentioned earlier.
All right, here's another one. Can you use the same amine solvent in pre-combustion and post-combustion plants?
That's an interesting one. The answer is no. Pre and post combustion plants use different solvents. By and large, pre-combustion systems use amine formulations, although physical solvents are also possible. And as I said, all the currently commercial post-combustion systems also use amines. But the amines that are used in either case are actually different chemically. They're different molecules.
All right. Ready for the next one?
Yep.
Can you remove SO2 in addition to CO2 in the same EFG plus absorber if there is a lot of SO2 in the flue gas?
Well, the flue gas cooling column, the direct contact cooler, can indeed be designed to remove SO2 prior to the SO2 getting to the amine absorber, and that is what we normally do if there are limited amounts of SO2 in the flue gas. If there would be a lot of SO2 in the flue gas, it may be more beneficial, and that is a similar story to what we just discussed on particulates. It is probably more beneficial to do a kind of a bulk SO2 removal upstream outside of the EFG plus plant, and to just have the flue gas cooling column doing the remainder, the polishing, so to speak.
All right. Boy, the questions keep flying in. On slide 36, which is the best amine system with respect to absorption efficiency? Which is the best amine system for the efficient CO2 absorption?
On slide 36, so this is showing post-combustion capture. Well, I mean, my answer would of course be that the best amine system in post-combustion capture is our EFG plus.
All right, very good. On slide number 20, how long is it estimated that CO2 can remain stored? Ultimately, will it be released back into the atmosphere?
In principle, forever. And yeah, the proof of that is not only in capture plants that have been operating in some cases already over decades. And some of the older of the existing operating carbon capture plants that I showed on the various maps, some of those have been operating for decades already. But additional proof of this is the fact that oil and gas reservoirs, they share pretty much the same geology as the formations where we would typically store the CO2. Those oil and gas molecules have also been sitting there since the time of the dinosaurs, let's say. So concern of the CO2 getting out should be mitigatable. Talking about geology, I refer to the so-called cap layer. That's an impenetrable layer sitting on top of the actual porous formation in which the CO2 would be injected. And it's that cap layer that ensures the CO2 will stay there.
All right, very good. On slide 30, with respect to ECONAMINE FG Plus, can you touch on the typical payback period as well?
Well, that is a very interesting question, very relevant. But I would like to say that it depends. It really depends on the legislative driving force. If you're in a situation where you're going to pay 100 euro or dollar per ton of emitted CO2, payback of ECONAMINE FG Plus post-combustion is going to be very rapid. It's going to be even better if you've got direct government subsidies that cover maybe part of the plant capital cost, maybe additional subsidies to cover the operating cost of the plant. And we have seen such subsidy schemes in practice. So it really depends on the specific location of the project, the jurisdiction, what exactly are the rules. And maybe a good takeaway there is to not only look at what are the laws today, but in what direction are they moving. And what we see consistently is that all the legislative pressure is only moving one way, namely to higher and higher taxes or fines, if you will, on continued CO2 emission. Other factors that really help improving the economic picture. I mentioned many of those. Being able to tap into a shared pipeline system is very important. A variety on that theme, by the way, is maybe being able to bring liquid CO2 to CO2 terminals. On an important project in Europe, a liquid CO2 terminal is under design development. So being able to tap in there is really helping out the economics, as is, and that was also discussed in the presentation at some length, a very good, clever integration with the host facility. That is another very important thing to maximize the payout of the capture project.
All right, great. Here's another question that's specific to the amine. Which amine system or technology has the minimum regeneration temp?
Well, that's an interesting one. Regeneration temperature depends on the pressure in the column. Most amines are aqueous solutions, so they boil at pretty much the same temperature. And the pressure is also typically in a similar range, let's say 1 bar gauge or so. So the answer to that question is mostly in the same range, call it 120 Celsius or so.
All right. Can you comment on the maximum absorption capacity achieved in amine commercial plants? Specifically, what are the grams of CO2 per liter of amine or per mole of amine?
I would say that really depends on the flue gas specifics. So I would prefer not to give out concrete numbers without having looked at the exact flue gas composition. Temperature is another factor, by the way. It really depends. It really depends.
Right. No, it's a good answer. Here's another one. In a pre-combustion approach for the hydrogen plant, is a CO shift a must for CO2 capture?
I would say that in hydrogen plants, you universally see CO shift. It's a very integral and important part of an efficient hydrogen production. So it's difficult to visualize a hydrogen plant without CO shift. So I've never seen a hydrogen plant without CO shift.
All right. Okay, the questions just keep coming. We're probably going to run out of time before we get through all of them, but here's a good one. Is Fluor investing in process intensification R&D to significantly reduce the size of gas-liquid contactors?
Yeah, we're continuously investing in developing the technology further. And had this webinar lasted for 2 hours instead of 1 hour, I would have been able to go in great detail through the ECONAMINE FG Plus flow sheet. And I would have demonstrated a number of design features that we can apply that can minimize energy consumption, minimize equipment size, and maximize energy efficiency. And all these features, we apply them on an as required or as applicable basis for different flue gases different quantities of flue gas, different CO2 concentrations, etc. And we see that some of these features can bring a lot of benefit or less so. It's a bit like a menu in a restaurant where we pick the right features to add to the flow sheet, depending on the specific application. Again, I think it's good to realize that flue gases are really quite different. As I said, the range of CO2 concentrations that we have seen ranges from as low as 3% to, in extreme cases, as high as 30%. So you can easily imagine what a difference that will make to the plant design. But for all of these concentrations, we can tailor the design to be most efficient.
All right, I think we have time for one more question. Wow, there's so many to choose from. Okay, here's a good one. To get an idea, do you know how many years of current industrial worldwide CO2 emissions can be stored in the underground injection fields?
Yeah, that's an excellent question. And the answer is that I don't have any numbers readily available to respond to the question, but what I definitely remember from having read about the estimated capacities of CO2 sequestration locations, plural, is actually that there is room, there is space, so to speak, for many, many, many years of storage. It's not as if this is going to run out of space in a few years or so, not by a long way. Having said that, maybe that's part of the background of the question, possibly. We see carbon capture as one part of the solution. Other parts of the solution are also valid. So imagine, for example, that a good part of the power generation industry is maybe going to be replaced by windmills and solar panels. So that in itself will greatly minimize CO2 emissions. But there are also going to be power plants that continue operating on, for example, natural gas. They're going to be needed to compensate for shortfalls in wind and solar power. And for those applications, carbon capture is a perfect fit, actually. So I would say that very different approaches can actually complement each other.
All right, Michiel, it looks like that's all the time we have for questions right now. Thank you so much for your detailed responses. There are more questions, so I hope you have some time later on today to work on getting the answers back so we can send them out to the attendees. To the attendees, we really appreciate everyone who attended today. You have been a very engaged audience, and it's been a pleasure being your moderator. We will be hosting our next webinar on Thursday, October 8th at 9:30 a.m. Central Time. In this webinar, Fluor Senior Fellows Nitin Geisis and Bill Bounds will discuss best practices for the modularization of rotating equipment. They will dive deep into the different types of modules, key benefits of equipment modularization, when it's best to modularize, as well as the technical features and principles to be followed during the design of machinery modules and machinery module structures. Keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for future webinars. Again, we appreciate your attention and thank you for dialing in. We will send out a compiled list of all the Q&As, including those that weren't answered, within a few days, along with a notification that the webinar recording is available for replay on fluor.com. If you have any additional questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back with you. From all of us in the Innovation Builders team, have a safe day.